When a localized wildfire smoke plume drifts over a dense commercial district, the exterior air quality drops to hazardous levels in minutes. Managing the air inside those structures is an $8.97 billion industry in the United States. That capital is deployed across a massive physical footprint, including 97.1 million residential homes and 5.9 million commercial buildings reliant on HVAC systems. Of that total market, $2.64 billion is concentrated in residential HVAC, while $4.73 billion is spent on air purifiers. The current operational standard for these systems is static. Facilities follow a calendar-based schedule, swapping out hardware filters every 60 to 90 days. This maintenance cycle ignores the volatility of outdoor air. A sudden spike in particulate matter or industrial exhaust requires an immediate mechanical response that a quarterly schedule cannot provide. Relying on regional air quality index data adds a second layer of failure. Broad averages often overlook street-level concentrations of pollutants sitting directly outside a building's intake vents. The result is a system where millions of sophisticated HVAC units pull in air while remaining blind to the immediate environmental reality outside. Transitioning these assets from hardware-based schedules to high-frequency address-level data networks is the central technical requirement for modern building management. To understand where the current architecture fails, we have to look at the specific micro-timeline of a localized hazard impacting a single address. Ideally, a building's ventilation system should react the moment a pollution spike registers outside. This graph maps legacy latency. A hazard spike hits at 0, but HVAC response delays 2 to 4 hours. During this critical window, buildings pull in contaminated air. Internal particulate levels rise, leading to health risks, productivity loss, and facility complaints. This delay also forces systems out of compliance with EPA and Energy Star requirements. Beyond the health risks, this systemic blindness creates a significant operational inefficiency. Operating with this level of latency results in a $272 million loss in incremental revenue for enterprise partners who cannot coordinate real-time responses to these events. Data latency is more than a health hazard. It is a structural failure that destroys asset value and blocks potential revenue. Solving this requires replacing regional sensors and manual inputs with direct API integrations that feed into building management systems. The architecture requires address-level precision to identify threats that broader zip code or county-wide averages miss. The Sparrow Intelligence Framework, shown here, establishes the benchmark for this high-frequency operational standard. To be effective, the system must maintain a 1 to 10-second update frequency. It also requires a 99.9% uptime SLA to ensure the network remains resilient during extreme environmental crises. This flowchart illustrates the network processing 50,000 data points per hour. The API routes triggers into the building management system to adjust ventilation autonomously. Secondary pathways branch into CRM and IoT platforms, providing full facility control. In this model, indoor air quality management becomes a high-speed data routing task rather than a purely mechanical one. Establishing a real-time pipeline allows the system to move from reactive mitigation to predictive intelligence. This is achieved by integrating 24 to 72-hour predictive forecasting directly into the API. This extended timeline shifts facility management away from emergency mitigation toward proactive inventory and service routing. This logic tree maps a 48-hour forecast linking directly to a CRM engine. It triggers proactive messaging, organizes service dispatch routes, and initiates automated filter upsells, routing inventory to the site before the hazard arrives. This predictive workflow captures the $272 million in revenue that was previously lost to system latency. Standard enterprise integration for this full API and CRM suite operates at $150,000 per year. Injecting predictive data into CRM workflows turns building maintenance into an automated revenue generator. Applying this high-frequency architecture across U.S. infrastructure reveals the full scale of the opportunity. This grid breaks down the market: 97.1 million homes, 5.9 million commercial buildings, 107,000 schools, and 6,100 hospitals. Institutional adoption is driven by regulatory requirements, specifically HIPAA and FERPA. These mandates project a 6 to 7. Using a hyperlocal API to replace regional data averages finally resolves the 4-hour latency paradox. The operational value of 97.1 million HVAC units is now dictated by the speed of the data pipelines that direct them. While legacy systems treat outdoor air as a threat, modern APIs process it as actionable data. In the next generation of PropTech, high-fidelity environmental intelligence serves as the mandatory control variable for the entire built environment.